Hello friends, welcome you all to the 15th lectures on function analysis and its applications. In this lecture, we will discuss the continuity of functions in non-linear spaces and some related theorems. These are the contents of today's lecture. Continuity of functions in non-linear spaces and some related theorems. Definition for continuity of non-linear spaces. If n and n dash are normed linear spaces, a mapping F such that n to n dash is continuous at the point x0 belonging to n if and only if to each epsilon greater than 0 there exists a delta greater than 0 such that norm x minus x0 less than delta. This implies that norm fx minus fx0 less than epsilon. Also we say that f is continuous on n if and only if it is continuous at each point of n. Meaning of this, limit x tend to x0 f of x equal to f of x0. Remark, we will utilize the following continuity criteria extensively. If n and n dash are non-linear spaces, a mapping F such that n to n dash is continuous at x0 belonging to n if and only if every sequence xn in n converging to x0, the sequence f xn in n dash converges to f of x0 belonging to n dash, that is xn tend to x0. This implies that fxn tend to fx0 as n tend to infinity. Theorem. Let n and n dash be non-linear spaces and let T be a linear transformation of n into n dash, then T is continuous either at every point of n or at no point of n. Proof. Let x1 and x2 be any 2 points of n and suppose T is continuous at x1. Then to each epsilon greater than 0 there exists delta greater than 0 such that norm x minus x1 less than delta. This implies that norm tx minus tx1 less than epsilon as per the definition of the continuous at point x1. Okay, equation 1. Now we can write norm x minus x2 less than delta as norm x plus x1 minus x2 minus x1. Here we have added x1 and subtracted x1, that is no change in this norm x1 minus x2 less than delta. So we can write this. This implies that tx plus x1 minus x2 minus tx1 less than epsilon as per equation 1. Okay. Suppose here the point x plus x1 minus x2. Okay. And it converges to x1. Since t is linear in the statement, so this can be written as tx plus tx1 minus tx2. Okay. So this implies that norm Tx plus Tx1 minus Tx2 minus Tx1 less than epsilon. So Tx1 Tx1 cancel out. We have Tx minus Tx2 less than epsilon. Norm x minus x2 less than delta, and this implies that norm Tx minus Tx2 less than epsilon. Okay. As per the definition of the continuity in non-linear spaces, this shows that T is continuous at x2 also. Okay. Since x1, x2 are arbitrary points, we have shown that if T is continuous at a particular point, then it is a continuous at all points. Henceforth, kernel of transformation. Let x and y be the linear space over the same field F, and let T such that x to y be a linear transformation, then the kernel of T written as curve T, and it is defined by curve T equal to x belonging to x such that Tx is equal to 0. That is, kernel of T is equal to collection of all those points of domain X such that Tx is equal to 0. Noting point, kernel of T is also called the null space of X. Here it will be X. Example, let R square R is vector space and T with the linear transformation defined as T such that R square to R square, where Txy equal to x0. Then find the kernel of the linear transformation. Solution. The given linear transformation is T such that R2 to R2, that is R square to R square, defined as Txy equal to x0. Okay, as per the statement. To find the kernel T, we need to find vector xy, which is the element of R2, such that Txy is equal to 0 to find the kernel of T. Okay. So Txy defined by order pair of x0. So x0 is equal to 0, 0. Therefore, x is equal to 0. There is no restriction on y. So y can be any real number. Therefore, the kernel T is order pair of xy belonging to R square, where x is equal to 0. That is 0y. Y is the element of R. Thus, the kernel of T is the y-axis in R2. Theorem. Let n and n dash be the nonlinear spaces, and let T such that n to n dash be a linear transformation. The kernel of T is defined as above. Kernel T is equal to x such that Tx is equal to 0 for x belonging to n. Then kernel T is linear manifold, and that kernel T is closed if T is continuous. Proof. Let xy belonging to kernel T and AB be any scalars, so that Tx is equal to 0 and Ty is equal to 0, because xy is the element of kernel T. Then Tax plus By. Here x, y belonging to kernel T, that is vector. So Ax and By also vector, and ax plus by treated as vector. So tax plus by equal to a tx plus b ty. We can write because here t is linear transformation. Okay, and here tx and ty 0. So a into 0 plus b into 0 is equal to 0. Hence ax plus by is the element of kernel T. And so kernel T is linear manifold, that is subspace. Now let T be continuous. Then since kernel T inverse of 0 vector. Why? Because here Tx is equal to 0. Okay, if x belonging to kernel T. Okay, then T inverse of 0 is equal to x. Definition is kernel T is equal to x collection of the point of domain n such that Tx is equal to 0. So here collection x, that is T inverse of 0. So we can write kernel T is equal to T inverse of the singleton set 0. And singleton set 0 is the closed set in n dash. We see that kernel T is closed. Noting point, every singleton set in metric space is closed and that the inverse image under a continuous map of a closed set in n dash is closed in n. Another way of proving this is as follows. Let x be a limit point of kernel T, then there exists a sequence xn in kernel T such that xn converges to x. Since T is continuous, Txn converges to Tx. But Txn is equal to 0 for all n, so that Tx is equal to 0. That is, x is the element of kernel T. Hence, kernel T is closed. Next theorem. Let n and n dash be non-linear spaces and let T be continuous linear transformation of n into n dash if M is the kernel, that is null space, of T, so that T induces a natural linear transformation T dash of quotient space n by m into n dash, and that norm T dash is equal to norm T. Proof. By the previous example, M is closed subspace of n and quotient space n by m is non-linear space with the norm of quotient x plus m. In quotient space n by m defined by norm x plus m equal to infimum of norm x plus small m, where small m belonging to capital M. Already it was discussed in lecture 11. We define T dash such that quotient space n by m to n dash by setting T dash x plus m equal to Tx, and so that T dash is linear transformation such that norm T dash is equal to norm T. Okay, by setting we have to prove norm t dash is equal to norm t. Let x plus m and y plus m be any two elements of n by m, and a b be any scalars, then t dash ax plus m plus by plus m equal to t dash ax plus by plus m. Okay, as per the definition of the coset, we can write this, and this can be written as tax plus by. Why? Because here t dash of x plus m is equal to tx. So here t dash ax plus by plus m. So we can write tax plus by. And in the statement t be a linear transformation. So it can be written as atx plus bty. Okay, applying this result, we can write at dash x plus m plus bt dash y plus m. Thus t dash is linear. Further, norm t dash equal to supremum of t dash x plus m such that x belonging to n, norm x plus m less or equal to 1. Why? Because here x plus m is the vector. Okay, so as per the definition of bounded linear transformation, we can write norm of t dash equal to supremum of t dash x plus m vector, where x is the element of n and norm x plus m less or equal to 1. Okay, so this can be written as supremum of norm tx, because t dash x plus m is equal to tx defined. So this can be written as supremum norm tx such that x belonging to n, infimum of norm x plus small m, where small m belonging to capital M less or equal to 1, equal to supremum of norm tx such that x belonging to n, small m is the element of capital M, norm x plus m less or equal to 1. Here supremum, here infimum, so we can write this as this one. Here without infimum, we can write equal to supremum norm tx plus tm such that x belonging to n, m is the element of capital M, and norm x plus small m less or equal to 1. Okay, we can write, because if m is the element of m, this implies that tm is equal to 0. So it can be written. So this can be written as supremum of norm tx plus small m. Okay, such that x is the element of n and small m is the element of capital M, and norm x plus small m less or equal to 1. So x is the element of n, m is the element of m. So x plus small m is the element of n. Okay, so by definition of m belonging to m, tm is equal to 0. So we can write this, and norm Tx plus Tm can be written as norm Tx plus m because T is linear. Okay, and x plus m is the element of n. Norm x plus small m less or equal to 1. So as per the definition of the boundary linear transformation, we can write this is norm T. Okay, because x belonging to n, m belonging to m, this implies that x plus m is the element of n. Okay, this completes the proof of theorem. In this lecture, we have discussed the continuity of functions in nonlinear spaces and some related theorems. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Naresy. Introductory function analysis with applications, John Valley and Sons, written by Erwin Krejcik. Function analysis, New Age International Publisher, written by B.B. Lemieux. And function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.